Alright, so a quick summary about gears. We've seen, let me do this. We saw three relationships. The first one was that the circular pitch of two adjacent gears should be the same so that they kind of match. If the circular pitch, which is just like this distance from here to here, is not the same to the next gear, there would be interference and it would just basically not work. So the distance from one tooth to the next is given by the pitch, the circular pitch, lowercase p, and that would just be the circumference pi d over n, the number of teeth. Full circumference divided by the number of teeth would give me that distance as an arc, but we usually don't use that. But we use the capital P, which is the diameter of the pitch, which is n over d, without the pi and the reciprocal. And if we're using international units, we use the module, which is d over n. So if p1, lowercase p1 equals to lowercase p2, because of what I just said here, we know that the diametral pitch and the module should also be the same. Basically, n1 over d1 has to be equal to n2 over d2. And we write this as n1 over n2 equals to d1 over d2. That's the first relationship. Second relationship comes from the fact that if one gear is rotating clockwise or counterclockwise next to another, basically like this, the distance that one gear is rotating here at the radius compared to the distance that the other one should be the same. Okay, so this is, I don't know, phi theta 2, and this angle is theta 1. Basically what I'm saying is that the arc S1 has to be equal to S2. Okay. That just means that if I divide by time, the distance from one gear and the other is the same, because there's no slipping here. And over time, in the same amount of time, that would just be v1 equals to v2, and that's angular velocity times the radius 1, angular velocity 2 times the radius 2. If I multiply by 2, this would just be the diameter of 1 and 2, and the angular velocity, if I divide that by 2 pi, which is the amount of radians per one revolution, this would be n1 and n2. Okay, and this one we write as n1 over n2 equal to d2 over d1. Okay, and that's the second one. And then the third one is that if we assume that the powers are the same from one to the other, so that they're 100% efficient, t1 omega 1 is equal to t2 omega 2. Again, just by changing omegas to revolutions per minute, we get this relationship where t1 over t2 over t2 is equal to n2 over n1. Okay, and we can put all of these three relationships together. Okay, so if n1 over n2 is equal to d1 over d2, that would be equal to n2 over n1, which is equal to t1 over t2. Okay, and this is basically all we need. By using the relationship between teeth or diameter, we can calculate the speeds of the different gears when I have a system of more than 2 gears. So as a simple example, if I have gear 2 driving gear 3 and driving gear 4, and then 4 is connected to gear 5, and gear 6. Okay. We can either have the number of teeth, so the information would be, for example, n2, n3, n4, or the diameters. Kind of doesn't matter, and you're always going to be able to measure, to count the number of teeth, or to have the pitch diameter of different gears. Okay, so if n1 and n2 is what's driving everything, I can do a simple calculation of the speed of 3 with respect to N2. So basically I'm just using this relationship between number of teeth and speed. Okay. From this I have that N3 is equal to N2 over N3 times N2, but and I can do the same for N4 and N3. Okay, for gear 4 and 3. So capital N3, capital N4, and we get that N4 is equal to N2 over N3 times N3, but N3 is this. I'm going to replace it here. N2 over N3 times N3. Sorry about these. This would be N3 over N4. And so same here. N3 over N4, then N2 over N3 times N2. Basically, I replace this by this. And so what we get, and we can, what we realize is that N4 and N2, the relationship between those two is a ratio between the number of teeth. And again, it can be number of teeth or diameters. So here we have that 3 is driving 4. 3 is driving 4. And 2 is driving 3. So here we have the driving gears, and here on the bottom we have the driven gears. But it can be the opposite if you just write N2 in terms of N4. Okay, it's not necessarily like that. Right. So if I have, for example, that I also know that N4 is equal to N5, and I have, and try to find N6 in terms of N5, this would be N5 over N6 times N5, but N5 is N4, but at the same time N4 is N3, N2, N4, N3, N2. Again, what I realize is that what I have here at the top is all the driving gears. So 2 is driving 3, 3 is driving 4, 5 is driving 6. And that's why I have 2, 3, and 5. And then at the bottom I have the driven gears, and 5 and 3, 4, and 6. Okay. So again, like if I just want, for example, N3 in terms of the rest. So I know if I'm starting from like N6, for some reason I know the rotation of 6 right here. It would be N6 times what? From the relationship, I know that there's going to be an N6 on the numerator, not the denominator. And N6 is one that is being driven. So I'm going to put all the driven ones, 6 and 4 up to 3, and then the ones that are driving, N3 and N5, right? Just as an example. So it's not an equation, it's just a relationship of the number of teeth to the speed. And once more, it can be number of teeth or just diameters, since this relationship between number of teeth and diameter is the same. Okay. Okay. Now there's also interest in the forces between one gear and the next. So if I have gear 2 and gear 3, and they are spur gears, let's assume the same condition I did before. So if this is rotating counterclockwise, this is rotating clockwise. If I isolate gear 3, and this 3, the fact that that one is rotating clockwise is because there's a force pushing it up. Okay, it's creating a torque that is causing that rotation, and we call that the tangential force, W with a superscript T. Okay, but because of how the teeth are made in 3, the involute profile that we talked about, the normal force has to be perpendicular to the surface right here. Okay, so it comes at an angle that we call the pressure angle phi, right? So because this is the total vector, there's going to be a component WT, but also a component WR radial going towards the center of the radius. Okay, and that's basically it for spur gears. I'm gonna do this not in the same orientation, but just a different drawing. If I have something like this with my gear, a spur gear still, okay, with all of my teeth, the tangential force that would be here is actually a distributed load. It's like a plane, right? So if I want to find or draw here the pressure angle, it would be something like this. The actual force in green is coming at an angle, and then the angle formed between these two, okay, is what I would call phi, right? This is going to help for the other types of gears, but this is basically what I would have. And there's no axial load in spur gears because there's no angle to it. So this is spur. We've talked about this 1,000 times, but once more here, we have we can calculate the torque that 3 is subjected to, because we usually have the power H. We know that the power is equal to T omega. So if the power for the system is the same in 2 and 3 and 4 and 5 and 6, because it's 100% efficient, so that's one of the assumptions, that would be power, sorry, I don't need that, it would be the torque of 3 times the angular velocity of 3, which would just be, if I want to solve for T3, it would be the power over angular velocity of 3, or power divided by N3, which is what I know, RPMs, times 2 pi. Okay, that would give me radians per minute. And then horsepower is usually in horsepower, so I need to multiply that by 33,000 to get pound-feet per minute. Since I usually use, if I do this, I would get pound force as my torque, as the units for my torque. If I want pounds per inch, I would actually be multiplying by 12 inches, so that feet cancels out and I get inches on the top. Okay, so I say all that to say that you can calculate T3. Now T3 is also going to be equal to WT at 3 times the radius of 3. So if I multiply this WT3 times this radius R3, that's what's causing the torque T3 that I can calculate. So in most cases, what I can calculate is the tangential force based on the power and the radius of the gear that I'm looking at, right? But I'm also interested in the radial direction, the WR or the WA, because those are going to transmit that force to the shaft and the shaft to the bearings, and that's going to be important. So let's look at another gear. If we have a helix gear, we have well, let me do this. Just have a gear from the side that looks exactly like the spur gear. Okay, and from the top, the only difference is that you would see an angle for the forces. So for the teeth, sorry. Okay. What this means is that the force that is on the plane of the screen will be going at an angle that has to be perpendicular to the teeth, because it's a normal force. Okay, it has to be perpendicular to the surface. So if this angle is psi, which is the helix angle, this angle is also psi. Okay, so if I were to draw that in a 3D version, something like that. Okay, and I have a left hand helix. Okay, I'm gonna have X, Z, Y. I'm going to have a force that is in the same plane as XY, okay, which is causing the tangential, the rotation. Okay, so if I was to draw the tangential one, just like I did for the spur gear, this would be WT, tangential one, times the radius R, whatever the radius of the gear is, that would give me the torque. That's why this is what I can calculate, WT. Okay, that would be located here. Okay, the component of the actual force that it's on the plane of the screen, meaning that there's another one that goes in the axial direction, because it's the axis of the gear. Okay, so this would be WA and this would be WT, right? So actually this would be the green one, and this would be the red one. Okay, like I said before, it's not just a point load because it's distributed on the teeth. Okay, so what I would actually have is something that is perpendicular, oh god, to the tooth. Okay, so if this is the tooth at an angle, I would have, yes, this vector that I can get the components of for Z and for X. Okay, same ones, WT and WA. Okay, but it's a distributed load, is what I'm trying to say here. Okay, the pressure angle is going to occur, and again, this is going to be important in just a second. The pressure angle is what's formed between the yellow plane of the distributed load and the full vector. Okay, so if I were to draw this as a 3D vector here, I have my yellow vector, my yellow vector here. Okay, that forms an angle of phi. And I'm going to redo this just so that I can show the 3D effect of the 3D helix. I would have still WT, WA, and then in blue a 3D one that comes from outside the page or outside the screen into that point, okay, in a 3D orientation, right? And the vector, the angle, sorry, that is made between this blue vector in 3D coming out of the screen into the screen and the yellow plane here would be phi, the pressure angle, right? So if I do a 3D version of those vectors, I'll get something like this. Let me do this. Oh, nope. That's better. I have my WA in this direction, WT in this direction. A yellow one goes to here, it doesn't have a name, it's just the vector that is perpendicular to the teeth, and a vector that is perpendicular to the surface of the teeth and occurs at an angle, so from here to here. This angle between yellow and blue would be a pressure angle, right? And this is all I need to understand so that I can write the different relationships. I can see that the yellow vector, let's say a vector V is the blue one, which is my full force, times cosine of phi. Okay. And if I want the red one, which is WA, this would be the yellow one times sine of phi, sine of psi, sorry, where psi is this. Okay, so basically this on the floor of that box. Okay, and then the last one, WT, would be equal to the cosine of psi, right? So this would be equal to W cosine phi cosine psi, and this would be W cosine phi sine of psi, right? I'm missing one more, which would be what? It would be the radial force. Okay, so let's do a purple one here, which would be coming in to the gear. Okay, purple one be coming into the gear. That would be equal to this side from here to here, which is just W sine of phi. Okay, and that's exactly what I want. I want the radial, the tangential, and the axial. Right? So I'm going to do one more, which would be bevel gears. So for bevel gears, in class I did a 2D version of this. So yeah. So something like this. If there's a gear that is rotating up, and then this is rotating left, you would see from that bottom gear that there's a force coming out that's making it rotate towards the left, right? So I can have my bevel gear like this, and I'm gonna do X and Z. X, Z, and Y. And this vector, let's keep the same colors to be consistent. I'll keep the green for the tangential one. So this vector coming out of there would look something like this in the Z direction. WT. Okay, that is what's making it rotate. That's causing the torque, and this is what I can calculate from what I said before. I have torque that is equal to power over omega, but that is at the same time the tangential force times the radius of the gear. This is what I can figure out in terms of everything else. So that's why that is the most important one. But like I said, and now it's why it's important that this is not just a vector but a distributed load, is that is already going to be at an angle. Okay, it's a vector, so there's no angle, but the distributed load itself is going to be at an angle, right? Just going to keep it like this. Now I know that angle is going to be something that I can calculate from the information of the problem itself. So if I do this correctly, I would see something. I would be able to get all the dimensions for this. So I can see something like this, something like this. And I would have a bevel gear that actually looks like this, right? This angle, gamma, can easily be found because I have, for example, the radius of this gear if I have the diametral pitch, and the radius of this gear if I have the diametral pitch. So if this distance is the same as this distance, then tangent of gamma is equal to the radius of I don't know, the gear and the pinion, whatever. Okay, this distance over this distance, opposite over adjacent for that gamma, and that's obviously going to be important. And what I said is that there's the force that I've been saying all along, is that the force needs to be perpendicular to the surface, okay, because it's a normal force, so a 90-degree angle, meaning there's going to be a component, a radial component. I used the purple one for that before, so I'm going to keep using it. A radial component here, okay, into the towards the center of the gear, okay, which is WR, and then a red one, which is the axial one. Okay, all those three make up the 3D vector, right? So I'm gonna do the 3D version for this. I'm gonna go back to my green. I'm gonna make it a little bit longer so that I don't run into problems. All right. So this is the green one, and I have a box right here. Okay. I don't know if that's gonna be enough, so I'll just do a separate one here. With the same green vector. I just want to not have the distributed load, but an actual vector. So this is my tangential force, WT. And if I look at this side view for the 3D version, I'm going to have an axial, this direction, and a radial coming in. So basically a radial coming in and axial coming down, right? Now the distributed load, the only reason I did the distributed load is because there's going to be a full vector. So the color that I used for that was blue, that comes from here to here. Okay, why do I say that this angle between the green, the tangential one, and the blue is phi in this case? Oops. So this is going to be phi. Why? Because it has to be in the direction of this distributed load. Okay, so if I were to draw the blue one here, okay, I'm going to have a distributed load as well. It has to come from the relationship between the green and the blue. Okay, let me redo those lines, because then it's not going to be very obvious. Right? This would be phi. And I'm practically done. Because if I already know what the angle is, and I can calculate this other angle that I mentioned before, gamma, right? I'm done. I'm gonna draw gamma here. From here to here, that's the right angle, and this would be gamma. Right? Easy. Green which is my WT, is equal to my full W, the blue one, times cosine of phi. The yellow one in this case would be this, would be, what did I use before? V. Would be equal to W sine of phi. And then the red one, which is W axial, would be V, the yellow one. And I want this component, so it would be sine of gamma. And the purple one would be the radial one, which is V cosine of gamma. It's this one, which is the adjacent to gamma, right? So this would be W sine of phi cosine of gamma, and this one would be W sine of phi sine of gamma, right? And that's what I want for all of them. So all I wanted for you to understand with the planes, with the distributed loads, is that it might not be super clear to some that the pressure angle is always between the distributed load that is tangential to the teeth or to the gear and the actual pressure, the angle at which the forces come. Okay. So if I got rid of all the black, I'm not going to be able to do this very easily, but this plane with respect to the plane that is tangential but also the plane that is parallel to the teeth but tangential to the gear, which is the green one, that and the plane of the full force is what I'm always going to call the pressure angle phi. Okay, you can see it from like the examples before as well. I need the simpler one. I have a red vector that is actually a distributed load, so it's a plane and it has to be tangential. Okay, so for spur gears this was pretty simple. Let me draw that. Okay, because the vector is not rotated, like it's not at an angle. It's just perpendicular to the teeth and tangential to the gear. Okay, and for this other one, I would have a vector in yellow that is perpendicular to the tooth, but on the plane that is tangential to the gear. Right? This one would not be very clear, but basically I would just be going up. Only up. Okay, so going up, I would find this. Where the angle between this line and this line, so from the side, I would see this line and this line, would be the pressure angle. Okay, but it's in a rotated plane. It's not the YZ. It's not this and this. Oh god. Y and Z. It's at an angle. Yeah, and that's why it's important. Right, let's leave it at that.